Alright gang, here we go. So this is Chem 2, Unit 5. Last video of the Chapter 8 material, we're talking about exceptions to the bond or the octet rule and bond enthalpies and how to calculate enthalpies of reaction using bond enthalpies. Alright, so first of all, exceptions to the octet rule. Now you might be asking yourself, why the heck would there be exceptions to the octet rule? Well, the reason is because the octet rule is kind of a garbage rule. All right, there's lots of exceptions, and it's not really, we talked about it when we talked about lattice energy, how the octet rule isn't really the real explanation. That's kind of a pseudo explanation of why bonds get formed, right? Bonds get formed because they're energetically favored, not because they have a full octet. So anyway, so exceptions to the octet rule is just kind of like, it's kind of an oxymoron a little bit. Okay, so here are the big three exceptions that the book talks about. All right, we got ions or molecules with an odd number of electrons. All right, that seems pretty obvious. And then ions or molecules with less than an octet, and ions or molecules with more than an octet. All right, those are your exceptions. So if you have an odd number of electrons, these are actually really, really rare. They're called radicals. All right, it's radical, dude. Anyway, so you got one electron that's chilling all by itself. Well, electrons always like to come in pairs, where you have one upspin, one downspin. So you very rarely have electrons that are where you have an odd number of electrons in whatever compound you're talking about. Almost always it's going to have some charge. So here's NO, okay, and so it's got this lone electron right here, and this is really unstable. They don't really last very long, and so essentially, in order to figure out which of these two things is going to be the more dominant structures, you essentially have to do Lewis dot or you have to do formal charges and then compare the electronegativities. All right, pretty easy stuff. All right, if you have fewer than 8 electrons, okay, this is going to be primarily this is going to happen in the second period before carbon. All right, so essentially this nails you down to lithium, beryllium, and boron. Okay, so lithium, we'll just go ahead and write those: lithium, beryllium, and boron. These are your big culprits of having fewer than 8 electrons. So BF3, okay, if you're going to draw the Lewis dot structure for BF3, you might have any of these 4 things. These are all resonance structures of BF3. Okay, now you might start by drawing these 3, right? And because in this case you've used all the right number of electrons and everything's got a full octet. However, if you were going to figure out the valence, or the formal charges on each of these guys, you'd find out, well, this boron has a formal charge of +1, right? 1, 2, 3, 4, so 3 minus 4. And then this fluorine is 0, 0, and this fluorine here would be -1, right? And then you'd have the same idea here: -1, 0, +1, and then 0, and then 0, 0, +1. -1. So those would be your formal charges. Now if you're going to do the formal charge on this guy, which probably based on our rules that we've talked about in the past would not be your first instinct, we'll look at these formal charges here. So boron here would be 3 minus 3, so it would have formal charge of 0, and then because all these fluorines here, the fluorons, all these fluorines here would have 7 electrons, and they came with 7, so they'd all have a formal charge of 0 as well. And we know that formal charges indicate that you have a more dominant structure when you have a lot more zeros, and when your more electronegative atom has a negative. All right, so because these has all zeros, this would be the dominant structure. Notice that even though this is the dominant structure, boron doesn't have a full octet. All right, it's only got 6 electrons. So this is kind of a little bit different. So that's, but essentially look, and whenever you see lithium, beryllium, or boron as your central atoms, start to be a little wary that you might start having a compound that's going to have 2 or 3 bonds instead of 4. All right. So anyway, so that's the same idea. Then when we have more than 8 electrons, this happens when your element is in periods 3 through 6. Okay, so remember that's the third row, so that starts with sodium, magnesium, all those guys, all the way down to cesium and barium. Okay, and so you have periods 3 through 6, and you can use your d orbitals. Okay, so your d orbitals, remember those are your transition metals, and these allow you to make more than 4 bonds. Okay, if you're at a lower energy level than 3 to 6, so if you're in 1 or 2, you don't have d orbitals available because 1 and 2 don't have d orbitals. Okay, those d orbitals, and we'll talk about this more when we get to the next chapter, allow your molecule in order to create new bonds that can bond in different ways than the standard 4 ways that you can get with s and p orbitals. All right, so here's PF5 and phosphate, 2 different examples. So here's PF5. Notice that we've got around our central phosphorus atom, we've got 10 electrons, right? So we call this guy hypervalent because he's got more than 4 bonds. He's hypervalent, all right? So this is kind of a 3-dimensional structure of what he looks like, and we'll talk about how these come about in Unit 9, or Chapter 9. Next chapter here. And then here's phosphate. If you're going to draw phosphate as just our standard way of drawing our Lewis dot structure, you'd come up with this guy here, right? You'd have phosphorus with the +1, and you have -1s all the way around. And then, but if you drew them like this resonance structure here, okay, and you figured out your formal charge, you see you actually get 2 zeros and then 3 -1. So this guy here is going to be your dominant structure, all right? So that's your dominant structure there, okay? Let's see. So a good rule of thumb, just to backtrack a little bit, if you have a negative formal charge on the central atom, okay, and a positive formal charge on the more electronegative atom, you're not going to fill the octet of the central atom. All right, I forgot to emphasize that. Okay, all right. So let's see. Oh, let's just do a couple of these here. So sulfur tetrafluoride. So this would be, so we'll do A, and we'll do like maybe C or something like that. So we've got, so it's got sulfur and 4 fluorines. Okay, we're going to test my math skills here. Sulfur comes with 6. Fluorine is 7, so 4 times 7. 4 times 7 is 28. Plus 6 is 34. So we got 34 electrons to work with. All right. So we've got sulfur, and then we've got fluorine, 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 and fluorine. Okay. We'll give everything a full octet. 6, and 1, 2, 3, 4, 5, 6. So we got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 total electrons we've used, but we needed to use 34, so we're going to put those last 2 electrons on our central atom there. And so this guy here, this is the Lewis dot structure for sulfur tetrafluoride. Notice that the sulfur has 10 electrons around it. Okay. All right, let's try one more. Let's try SOF4. All right. So we've got SOF4. So we've got a sulfur, we got an oxygen, we got 4 fluorines. All right. Sulfur's got 6, oxygen's got 6, and then fluorines are 4 times 7. All right. So this is going to be the same as what we had up here, but with 40 electrons. All right. Plus 6 more from up here. So sulfur is going to be in the middle because it's the least electronegative. So we'll put sulfur, and then oxygen, and then we've got the 4 fluorines attached to it. Okay. All right, and then we'll give everything a full octet. 2, 3. All right. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. So you might be thinking to yourself, oh, this is pretty good. We've used 40 electrons. We had 40 to work with. So this must be the Lewis structure. But let's pause for a second and figure out our valence counts here. All right, so all these, the fluorines are easy. They're all going to be 0, right? They're just 0 because they had 7. They have 7 now, so the formal charges of 0. Now the oxygen here would have it brought 6, but now it's got 7, so that has a negative charge, of -1. And the sulfur brought 6, and it has 5, so this would be a +1 for the sulfur. Okay, so it's still not that bad, right? We got 4 zeros, a -1, and +1. It's not that bad. Let's see if we could just be a little bit more creative and see if we could come up with something different. So if we have sulfur, and instead we give it a double bond to this oxygen, all right? And we'll do the same thing around all the rest of them. We'll put our lone pairs around them all. All right, and then count them up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Now notice we've used exactly the same number of valence electrons in this structure, and all the outer electrons or outer elements still have a full octet. However, sulfur now has 10. So let's figure out the formal charges for these guys. So fluorine has 0, right? There's still 7 and 7, so 7 minus 7 is 0. This oxygen brought 6, and it has 1, 2, 3, 4, 5, 6. So it has a formal charge of 0. And the sulfur brought 6, 1, 2, 3, 4, 5, 6. So it has a formal charge of 0 as well. So 0 is all around. So that means this guy here has to be, this is excuse me, that is your dominant structure for this guy here, SOF4. All right. Now we're going to change pace a little bit. We're talking about average bond enthalpies. Now first I want you to understand something. When you took freshman biology in high school or sophomore or whatever it was, okay, you got lied to. You were told that when ATP creates energy, you break that bond, you get energy out. Now that's not really true. When bonds get broken, they never produce energy. Okay, anytime you're breaking a bond, you're always using energy. It's an endothermic process. It always takes energy to break bonds. The reason breaking ATP ends up giving you energy is because it forms ADP, which is at a lower energy state. And so you're starting at something that has high energy state, right? And then you're breaking it, and so then it breaks down into ADP. And then so you end up with that difference in energy is the energy you get out of it. Okay, and so that's what your biology teacher probably meant if you got taught that. All right, is that difference in energy is really what's going on. Okay, however, so breaking bonds is always an endothermic process. It's always going to take energy in order to break bonds. So because of that, we can come up with these bond enthalpies, okay? And this is the energy in kilojoules per mole. So how many kilojoules per mole of that bond does it take to break them, okay? So these are average values, all right? So it's kind of a run-of-the-mill. And if you look online, you'll actually see that these values kind of change drastically from place to place, just kind of looking at where they got their data, how they got their data, so on and so forth. There's kind of, different discussions about which way is the best way to find your average and so on and so forth. So just if you're using this table off this PowerPoint, I don't recommend it because their notation is a little funky. These little L-shaped things are single bonds. Okay, so if you break a CH bond, it takes 413 kilojoules per mole. If you break an NF bond, it takes 272 kilojoules per mole. So on and so forth. Over here, we've got more single bonds listed out, and then we've also got multiple bonds. The quotation marks, the 2 marks here, these are double bonds. So this is a C double C bond. That's 614 kilojoules per mole. And then the comma is a triple bond. So that'd be your 839 kilojoules per mole. Notice that your single bond, so single CC single bond was over here. Right here, it produces 348. You need 348 kilojoules per mole in order to break a CC single bond. In order to break a CC double bond, you need 614 kilojoules per mole. In order to break a CC triple bond, you need 839 kilojoules per mole. All right. So you can see that multiple bonds are stronger than single bonds. It always takes more energy to break a triple bond than a double bond than a single bond. All right, in that order. Okay, and then they also correlate to bond length. The triple bond is shorter than a double bond, which is shorter than a single bond. So you can see here on this graph that as our bond length gets shorter, we get triple bonds, right? We're going to the left on this graph, and then as our and then as we get more triple bond characteristic, we end up with a higher enthalpy of bond enthalpy, excuse me. All right, so it's pretty simple. Now let's just take this data here for a second and go for a spin. Okay, so we're going to use this data in order to figure out the bond enthalpy, or the enthalpy of reaction in kilojoules per mole of a reaction. So let's say that we're starting with ethane. So we're going to start with ethane. That's C2H4. And we're going to combust it. We want to know how much energy we're going to produce. Okay, so it's a combustion reaction, so we're going to reaction with oxygen. I'm not going to bother writing states because it's not that important here. All right, so we're going to combust this guy. So it's going to form carbon dioxide and water. Okay, Okay, we want to find our enthalpy. So that's our delta H value. What is this enthalpy in kilojoules per mole? And so let's balance this guy real quick. So we got a 2 here. Hydrogen's 2, so we need a 2 right there. So 4, 6, so we need 3 oxygens, right? Okay. Now, whenever you're figuring out these guys, your basic formula to solve this is that your delta H is going to be equal to the sum of all of the bond enthalpies of the reactants. Okay. The bond enthalpy of the reactants minus the sum of the bond enthalpies of the products. All right. So in order to do this, we need to figure out what bonds we made or broke and all these things. So one way to do this is just to write out real quick exactly what these structures look like. So ethane looks like this: C, C, and then H, H, and then this H here, and this H here, and this H here, and this H here. Lots of CHs. All right, and then, so we got one of those, and then we got 3 of oxygen. Oxygen forms a double bond. Notice I'm not going to bother writing in these the lone pairs because they don't mean anything to us because we're talking about lone pair, or we're talking about the bonds. That's what we care about. And then we've got 2 carbon dioxides, right? So we got an oxygen, carbon, oxygen. So that's our carbon dioxide. And remember, like if you don't remember what these are, you know how to draw these structures now. It's just Lewis-Dawes structures, okay? And then 2 waters. So we got H and O and H, right? So those are our bonds. So in order to find our delta H, we need to find all the bond enthalpies of our reactants. All right, so delta H. So I've got another graph here pulled up that I'm going to use. These values, I didn't really check them versus the ones that are in the textbook. So they might be slightly different, but they should be fairly close. All right, so we're going to find the bond enthalpies of all the reactants. All right, so we've got 1 ethane. All right, so this is our reactant. So in our ethane, we have a CC bond, right? We got a CC bond, and we've also got 1, 2, 3, 4, 5, 6 CH bonds. Okay, so that's in the ethane. All right, so maybe we'll put this in its own big parentheses. So that's the ethane, and then we're going to add in the ones from the oxygen. Now there's 3 OO bonds in the oxygen. All right. Dang it, 3 OO bonds. All right, and those are our reactants, okay? Then we're going to subtract out the bond enthalpies of the products. All right, so we'll put a big bracket, and so we've got 2 carbon dioxides, right? So we'll say 2, and inside each carbon dioxide we have 2 CO bonds. Oops. Right? Does that make sense? So we have, there's 2 carbon dioxides, and inside each carbon dioxide we have 2 COO bonds. All right? And then we also have 2 water molecules, and each water molecule we have an HO bond or an OH bond. All right? Same difference. All right? So that's that. So in order to find our delta H now, all we have to do is take these exact same things and just write in these values. So we go to our chart, we find a CC bond, and it says it's 346 kilojoules per mole, so we'll write 346, all right? And then we'll add in 6 times our CH bond, so we find CH, it's 413. Remember, I'm not using the ones from before, I'm using this other one I found online real quick. All right, so 3, and then 3 OO double bonds, so they say that's 498. All right, 498. Okay, and then 2 times our COO bond, 799. All right, and then plus 2 times our OH bond, 463. All right, so our delta H. Now, now if you think about this, if we're burning ethane, you should automatically know this is a combustion reaction, so it should be an exothermic reaction. Now, before we plug in any values, we can just kind of make sure that we understand that if our values are correct and we set up everything correctly, that our change in enthalpy should be negative. Now, this is the test. This is nerve-wracking because I didn't test these numbers beforehand, which might not have been the best idea. But it is what it is. Okay. All right, 346 plus 6 times 413 plus 3 times 498. So on the reactant side here, I got 4,318 kilojoules per mole. So now we're going to subtract out the product side. So that's 2 times 799 plus 2 times 2 times 463. Please let it be bigger than 413. Oh, good. Or 4318. I got 5,048. Right? So then we can take those two values. We'll say 4318 minus our 5,048. We get negative 730 kilojoules per mole. All right, so that's how you use bond enthalpies in order to figure out your enthalpy of reaction. And like we did it with a combustion, but really you could do it with any reaction. You know, as long as you've got the values for bonds that are formed and broken, you can add them together, multiply them by however many you have, and Bob's your uncle. All right, so anyway, so that's the end of Chapter 8 material. Congratulations, we made it through another chapter. We'll just keep on keeping on. Let me know if you have any questions, and I'll see you on the flip side.